All right. Hello? Okay, good. It's working. We are on time. All right. Ba, 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 ba. All right. Um, should we start? Should we start? Why not? All right. So today, this is an extra cord. That's not relevant for me right now. Okay. So today we have a little bit of a shorter lecture, so that should be nice ahead of the weekend. Um, we are going to start our discussion of linear regression, and specifically, I want to say this is the first lecture in linear regression, so 1. And then we will do a couple preamble or preliminaries, talk about linear regression, introduce it a bit, and then next week on Tuesday we will go a little deeper into linear regression and how you use it for classifications and what the limits of linear classifications are. Sound good? So today, I forgot to change this. Well, oh well. Today you have lots of exciting things to go on. Okay, now you guys get a glimpse on my lecture creation process. Um, okay, so let's start off with the main idea behind linear regression. And let's say we have the following graph. This is a couple little data points. You have some data here, and you have some data, and you plot it out, and you see, it follows a pattern, as hopefully most of your data follows. That would be horrifying if you plot it out and it's all completely random. You see a bit of a pattern here, so you want to create a model that predicts this data, right? So, a few bits of terminology. You have a couple outcomes, also known as targets, that are all real numbers. 4 covariates, also known as inputs, that are along the x-axis, right? So you have an input x and you have an output y. That's what the data tells you, or that's what you measured. That's what you measured, and it will plot it here. And you want to basically create a model that will give you a prediction given the same inputs, right? So, of course, depending on what you're doing, depending on what you're doing, your data might not be perfect. This data doesn't look very perfect. It looks like there's some pattern, but it does look like there's some randomness in here. So we need to figure out what the underlying system model is and what the parameters for this model are. All right? So the first choice we have to make is, what model do we choose? And our choice for this lecture, given that the title of this lecture is linear regression, I think we could safely assume maybe a linear model, right? So we have a graph. We assume a model that's something along the lines of y equals mx plus b. And then, if you're anything like me, you're not even going to bother writing a fitting script. You're just going to try to put a bunch of lines, overlay them on top of the graph, and see what works well. And in fact, some lines work better than others. You have flat line with basically zero slope that doesn't seem to fit at all. So positive slope seems to fit. If the slope is too big, for instance 6x, that's not great. If the slope is too small, seems to diverge also. Somewhere around 2 seems to be correct. And you have some offset, right? Some linear offset, namely b, that seems to be correct. namely 5, that seems to work fairly well, right? So that's how we would do this manually using our own massive pattern recognition brains. But the question is, how do we communicate the best fit to a computer? How do we have the computer find the best fit? So we're assuming a linear model again. Oh, there we go. I'll zoom in. Assuming a linear model. And in this case, we're going to say y is the prediction, and w is the weight or weights, and b is the bias. So for right now, for this lecture, we're going to assume a one-dimensional input, i.e. x is just a scalar. The next lecture, we're going to expand that to multiple dimensions and so on. But for right now, let's keep things simple. We have one input x, and we want one output y. And we have two parameters. One is the slope, and the other is this offset factor, this linear offset. So how do we measure how far or close one set of parameters is to the data? And so before we go too much further, let's just get a couple of database notation. Let's just get a little bit of notational info out of the way, namely that the points that we saw previously, these points right here, this is what's known as our data set. This is what's known as our data set. And the data set is simply a tuple of the inputs and output of a bunch of different measured points. Okay? And typically the way we describe each particular point, each particular element in the data set is with this superscript, namely the parentheses I. That describes, okay, this is the 0th data point, this is the first data point, this is the second data point, this is the ith data point, this is the last data point. Okay, makes sense? And you have, of course, and assuming you have n data points. Also, the input is simply a bunch of real numbers. Yeah, it's always a bunch of real numbers of some particular dimension. So the number of input variables you have, this a real number, it's a combination of d real numbers. Okay, so in this case, we're going to use just one dimension input. So so the data is simply x is some real number. So again, the question is, given the unseen data x, how do we predict y? Okay. So we introduced this function last time, but it's always nice to refresh our memories. Namely, we have a loss function, the least squared loss function, that is, the squared error loss function that's simply y minus t squared. Okay, and that's better. And I'm including this 1/2 vector. I'm concluding the 1/2 factor just because it'll make gradient calculations cleaner a bit later. You know, if we take the derivative of the loss function, then this 2 comes down. And so instead of having a floating 2 constant in all our gradients, this 2 comes down and sort of cancels out with the 1/2. That makes our calculations nicer and cleaner. And so I just included the 1/2, but it doesn't really affect anything, right? Remember, when we do what we're doing, when we want to match a function to the data, is we want to minimize the distance between the data. So it doesn't matter. So, maybe I'll. Come on. There we go. Oh, there we go. So we have a particular, so we have our data in blue dots, and we have our line guess. We have some guess that we input, right? We'll start with a random slope and a random bias. And what we want to know is how far away the line, the predicted values, are from the actual measured values. So what we do is that for every data point, we measure the distance from the point to the line. That's pretty simple, right? That's our distance term right here, y minus t. That's the dashed line in red, y minus t. And then we square it. Why do we square it? Because sometimes the distance is positive, sometimes the distance is negative. So in order to, I mean, we don't really care if the distance is positive or negative. We just want the distance to be as small as possible. So it's a good idea just to square it, get things all into even space, get the loss completely positive in order to minimize it. And then what we do is calculate the loss for each one of these data and try to minimize it. And so back to the point about the 1/2 factor, it makes things cleaner because it'll cancel out the 2 when we take the gradient of the loss, but also it doesn't really affect anything, right? Minimizing 1/2 x is the same as minimizing x, right? X would still be equal to 0 in both cases. So since we don't really care about the absolute loss value of the loss doesn't really have any physical meaning. All we care about is minimizing the loss. So since all we care about is minimizing things, since all we care about is the relative value of the loss, we can multiply it by any factor and it won't really change things. And doing the things this way makes our lives a little easier. Does that make sense? Yes.
Is there any advantage to squaring the error instead of keeping the absolute value, or is it just easier for calculations?
Easier for calculations, yeah. Yeah, and we're going to go into different loss functions also, which we'll use eventually absolute values and stuff, but yeah. Yeah, so this is the loss function that we start out with also because it's very easy to calculate the gradients for this. It could get a little hairy later down the line, which is why PyTorch exists because some of the loss functions people use, you don't want to actually have to calculate it by hand. Okay, so depending on the values of the loss we choose, depending on the values of W and B we choose, the loss can differ significantly. Actually, let me make these images a little bigger. It's always a problem because when I'm on the Jupyter Notebook, when I open the Jupyter Notebook, the default, okay, fine, don't do it. Don't be nice. All right, my computer wins. So the point is, depending on the values of W and B we choose, the loss can differ significantly. So again, we remind ourselves that we had a previous graph where we just guessed a bunch of possible lines. So this blue line had a very small loss function because the distance from the blue line to any one of these data points is fairly small, right? Seems like a good middle of the road estimate. Other things, for instance, this green line, the distance between the green line and these data points is kind of significant, especially towards the data points that have larger x's, right? So the loss, so we have two variables. We have two variables, W and B, that can affect the loss. So of course, the loss becomes a 3D plane. And instead of plotting an actual 3D surface plot, which is hard to read, we plot a contour plot, a little easier to read. And we just show that depending on the value of the slope and the bias, we get a different loss amount. Right? And so if we look at this, gradient, if we look at this loss function, the place where the loss is minimized becomes fairly clear. It's somewhere around here, right? Maybe not completely on B. There was a bit of, I generated that data set by adding some random noise to basically B. So there is some, it's not completely dead on this line, it's probably around here. But this is about where the loss is minimized. Then we got a bunch of our other guesses. For instance, red, which is close to B, but it's still larger than the minimum loss. And if we look at it here, we see that, yeah, this line is sort of like B. I mean, it has a very similar slope. It has a similar bias, but it's not quite right. So that makes sense. This red line having a similar loss, but not quite as small as B. And also, again, like we mentioned before, this green line, if we would have a huge loss, and what we see right here is actually the loss value for the green line is way out there. Okay, so we have a function, we have a space, we have a parameter space. Okay, this is what's referred to as a parameter space because, well, we're evaluating the loss with respect to all the possible parameters. Lucky for us, we only have 2 parameters at the current moment, so we could visualize it easily. Once we get to, thousands, millions of parameters, I mean, we won't be able to graph that out cleanly anymore. But for the moment, while we're learning, nice way to visualize things. So what do we know? What do we want to do from here? Well, we have this parameter space, and we have this parameter space that for any given set of parameters, for any given set of parameters, for instance, for a slope of 0 and a bias of 0, you get a particular loss right around 150. So in this case, what we want to do is very simple. We just want to find the values of M and B that minimize this loss. We want to find this minima, right? We want to find the point at which the gradient of the loss is equal to 0. Make sense? Oh, yes, please. Oh, good point. Yes, the loss that's being plotted here is the summation of the loss of all the points. And I didn't put that here. Oh, bad me. I should have. Oh, no, it's cut off. That's why. I was like, I swore I put it there. Okay, yes. So we extend the loss function to be the loss for the summation of all the points. Thank you for catching that. Thank you. Yeah, so same idea as here. We have the loss function for an individual point, and then just for each particular points we have n points. For each particular point, we calculate the loss. We add it together, and we get the total loss. The total loss of the current function, of the predictive function, with respect to the data set. And what's important here, we have the predicted value, y minus t. We could expand this out a bit and to be wx plus b minus t. Okay? And of course, xi is the inputs for each data points, and this is a predicted value, and this is the target. Or, I think of it as the ground truth value. Okay? T stands for target. Y stands for the predicted value. Other notations I see a lot in literature are, I see a lot of people using y underscore p for predicted value and y underscore and just y for target value. This is one of those things that notation is notoriously inconsistent, especially specifically with this y t, y p, y. I've seen even A and B. So there's no standard notation, but this is the one I'm using in this lecture, and hopefully you guys will be able to figure it out in other papers. Okay. Other important thing is, in some paper, right now I'm using predicted value minus target. That'll give you the loss. Other papers use target minus predicted value, but really that doesn't make a difference, right? If you multiply these two values by -1, really you're not doing anything because you're squaring them anyway, so that -1 factors out. Okay? Everyone with me? All right. Yes, so So we have, oh, see, I should have just zoomed in. Okay. Okay, so we have a bunch of guesses. The guesses give us some particular loss value. And we know, well, yeah, we know this is a convex. We know linear, well, I'll tell you, linear, I don't know if I showed it last time. I mean, we're not doing proofs. So we know linear systems are convex functions, okay? So the beauty of a convex function, as we remember last time, is what? Is that it will optimize very well. That's really the beauty of it. Most algorithms are optimized very well on convex functions. So, and convex functions always have one global minima. That was the thing I wanted to say. Convex functions always have one global minima, which is right here. So we got to find a way to get from any random guess down to the minima there. Okay, makes sense? Okay, so this is our optimization problem, and we got to solve it. So let's solve it, and let's start off, as we always do, with lots of notation. Oh, I should have made it the fancy L over there. It's okay. So we have a loss function. We have, and this is the generalized loss function. This will become relevant, especially next week when we talk about multi-dimensional linear regression. But we have a loss function where we have a bunch of weights times b. And in fact, let me write this out. We could say, assuming y is equal to w1 x1 plus w2 x2 plus l dots plus b. Okay, assuming a multi-dimensional linear regression, we have this particular loss function. Okay, now in our case, we only have one weight, which is nice. But writing this out, we have each of the weights. Writing this out, we get the loss function. We have the predicted value minus the target value, and then we want to get the actual. And then we get the actual loss function, which is the sum of all the predicted weights, which is the sum of all these linear features, plus the bias minus the target for every single one of the data sets. Okay, and so if we want to actually what enable diction? I don't know why that keeps coming up. We want to actually do that. We just say the sum is equal to w times x I, and of course, I forgot the w times xi linear regression. Okay? So, does that make sense? We go from multiple dimensions down to the one dimension we're using. And now, what do we do? Well, what did we do last time? What do we do with this loss equation? Same thing we did with last time. We basically calculate the partial derivatives with respect to the parameters and solve for the parameters w and b. Make sense? All right, so let's do that. So let's simplify the linear equation. And let's simplify it in a way that will help us later on. Namely, we have two parameters, wx and b. But let's generalize this a bit. because really it would be very, very nice to not have two different parameters we're constantly worrying about. We would be nice to just sort of optimize for a single variable, right? To derive with respect to a single variable, to optimize for with respect to a single variable, okay? So instead of saying y equals wx plus b, let's say y is equal to w1 x1 plus w0 x0, where x1 is the original data point and x0 is 1, always, okay? So doing this allows us to write y is equal to wx, where w is equal to w1, w and the bias, which is equal to the w and the bias, and x is equal to 1 and the actual parameter x. Okay, so multiplying these two together gives us b plus wx1. Does that make sense? This is the only little confusing step that you have to sort of tolerate, and then the rest of the derivation becomes very simple. Okay, but I'm doing this because it makes the rest of the derivation a lot cleaner, and this is more what you see in literature in textbooks. So I want to get some consistency with other resources you see outside of class. Okay, you guys with me? So we're rewriting this equation just in a simpler form. It's effectively the same equation, but instead of having this bias parameter and a different slope parameter and a bias parameter, we have just multiple slopes, and we just say the last value of x is 1. Okay, x has two values: one the actual data value, and one the actual just the value 1. And so when you multiply these things together, you still get wx plus b. Okay. All right, so we have the loss function as before. Namely, we have loss y of t. Loss is a function of y and t, and which is the sum for all the data points of the predicted value minus the target value squared. And then lastly, we know y is simply the sum of all the w's times their respective x's minus the targets square. Okay? So little bit of notations, but nothing too hard. And so if we do the partial derivative of this equation, if we actually take the partial derivative of the collective loss, epsilon, with respect to w, then we get, with respect to a particular function, we get the, with respect to w, I should say, with respect to w, we get something very simple, right? We get the same thing that we would expect to get in just normal calculus, namely, collective with respect to w is the sum of all of the actual value of x of j. Oh no, that was w of j. Sorry, I keep going back and forth. Yeah, that was w of j. I was right. The sum is you simply use the derivative. You use the chain rule. This exponent 2 comes down, cancels out this 1/2. That's why the 1/2 was there in the first place. And then we take the derivative with respect to wj, which is simply x of j. So the total derivative for each point becomes the error, the target minus y, also known as the residual. A lot of people call it the residual, times the actual input, and the sum of that for all possible inputs. Okay? All right. So nice little clean function there for the most part. And so we have the partial derivative of this function, like so. And when we expand it out, namely, when we expand y out, we get y is simply the dimensions, the number of dimensions of the linear function, w of j times x of j, for every data point, for for every data point, right? This is just the number of dimensions. And in this case, since we defined x as one data point, there would be 2 dimensions for this. And so the sum of those minus the target, then multiplied by the rest of this, would be the total loss function. Would be the partial derivative of the total loss function. Okay? And then doing a bit of organization, like so, you could reorganize this whole expression. You could reorganize, you could carry out the multiplication. You could expand out the multiplication. You could multiply this term times the target and this term times the actual equation y to get the total, the partial derivative of the loss function with respect to a particular weight is equal to the number of dimensions times the number of data values of x times itself, of x of j times x of j prime, times wj minus 1 over n x of j times the target. Okay? So, not a hard equation. It looks a lot more complex than it is. But this gives us the gradient of the loss function, right? So it's very important that we got the gradient in this term. We could have stopped here, and actually, I'm gonna come back to this actual function here. But even if we stop here, we have the actual gradients, and with the actual gradients, we could do a lot of nice stuff, right? So how do we use the actual gradient of the loss function? Well, given the last lecture was all about gradient descent and modifications to gradient descent and all of that, it seems natural that we would just try to use gradient descent, right? To calculate the optimal value of the slope and bias just iteratively, right? That would be step 1. I mean, why bother trying to get an analytic equation if you have gradient descent? So let's do that. Gradient descent is simply the idea behind gradient descent. We have a weight, we have a parameter, and we adjust the parameter by having some learning rate and multiplying it by the gradients. And in our case, just to keep things a little simple, I'm not going to go down that super complex equation. I'm going to go to a simple equation, just calculate y minus the target, and that will be the gradients with respect to a particular weight times alpha. Okay? So let's just test it out. So let's look at a little bit of code. And so this part here, by the way, you guys, I include the code because I really want you guys to mess around with it. Please do. This little part here is just to generate just to generate the sample data that I'm using through the lecture. So not too important. But most important things is we have inputs, we have targets, okay? So the one thing I did, remember I said that I want x not just to be the actual input, I want to actually put a 1 there. I want to actually put a 1 there for the bias, so that's all I'm doing here. I'm creating a vector of 1s and just appending it to the actual input vector, okay, to get that matrix version of x. And then I initialize the slope and bias to 2 random numbers. This is from an old W, B. And this is just information for tracking. And so all I do here, y is equal to mx plus b. So I know that the gradient is simply equal to the gradient minus some alpha times 1 over n of the sum of all of the y's times x minus t. Or all of the sum of, the y minus t times x. Okay? That's all we're doing there. it's kind of nice to use torch and have all that matrix math done for you, because you don't have to have summations and for loops everywhere. But I promise, if you want to test that out and include it and like do it the brute force way with lots of for loops and stuff, I encourage you to do that. But hopefully that makes sense. And we're zeroing out the gradient. And actually, this step isn't completely necessary, at least not for this case. Sometimes it becomes necessary, but not right now. But still, it's nice to do it. And then we're just recording we were recording the slope and bias values at every interval. Okay. And in this case, the iteration we're doing like 5,000 iterations. This is. We'll come back to why I chose that big of a number. Okay, so we ran the code. I ran it already. Okay, and we start out with some initial guess. Come on. There we go. Started out with some initial guess, namely, we start out bias is equal to 2.5, and the slope is equal to negative 0.6. Yes, negative 0.6, negative 0.65. And then the final guess is the bias is 5, and the slope is equal to 2, roughly, which I think makes sense, right? So as you'll see, the way I generated the data, I just assumed a true function of 2 and 5 for the slope and bias, and then I added some random noise to it. But I think because I added random noise to it, then it sort of shifts the optimal function around a little bit because it's random. So, and it's only 10 points, so you're going to get a little bit of, you're not going to get dead on the average. So that's why you're getting a slope that's little above 2 and a slope that's a little above 5. Okay, but otherwise, the whole thing seems to be working well, right? Yeah, and so this is using the manually calculated gradients. Now, what's the beauty of PyTorch? The beauty of PyTorch is that we don't have to manually calculate the gradients. And so I also modified this slightly. Come on. Yep, speaking, do we even need to really calculate the gradient? So this is basically the same code, but the only difference here is in the for loop where, there we go, where we don't even bother calculating the gradients. We just calculate all the errors, and we just do the loss function directly, right? So remember what we did in this step. Oh, maybe I should go over. For the two parameters, w, we simply initialize them to some random numbers, but also we set the variable that it requires the gradient equal to true, right? That's the most important thing. That's how you tell Python that you want to calculate the gradient later. So we do some calculations, and we literally, this is the target minus mx plus b. I reversed that a little bit. I could have done the mx plus b minus target, doesn't really matter. And then I calculated the loss, which is simply sum of the errors squared over n, same thing. And then I simply asked PyTorch to backpropagate and calculate the gradients. And then when I wanted to find new values for m and b, I just said alpha is equal, w is equal to w minus alpha times the gradient. Okay? And we literally get, if we do it out, if we run the code, there we go. If we run the code, we get roughly the same values, not exactly the same. I could run it for more iterations, but why bother? The point is made. We get somewhere along the lines of 2.0. I think last time it was 2.05. Now we're getting 2.04, roughly the same, with also a bias of 5.6. And again, if we check the actual line, we see that the line starts out at nothing. That pretty much completely wrong. What was the initial guess? Oh, the initial guess was the slope was negative. Yep, slope was negative, and the bias was also negative. So we start out with a line that's initially wrong, that's completely wrong, and then through multiple iterations, we go towards a line that's more in line with the data. It's pretty much bang on. And as we see, the loss, the mean squared error, continues to decrease with every iteration. First greatly, first suddenly, and then sort of exponentially. Make sense? What else is there to say for this? Oh, before I move on, and maybe I'll mess with this a little bit. Why did I choose such a large number of iterations? What's the alternative? Instead of doing a ton of iterations, what's the alternative to just thousands of iterations? I mean, this doesn't tax my computer at all, so thousands of iterations doesn't bother me. But assuming that each iteration was costly, is there another option to make this to keep the number of iterations sort of small? Yeah, the learning rate, right? So let's try to make the learning rate a little larger. Yeah, let's just multiply by 10, and there you go. Huh. Oh, Torch. I still don't understand why the first time you load Torch, it takes so long. Yeah, and something breaks. Why is it doing this? Why when the learning rate is large, does the whole thing kind of break down? Yeah, it's unstable, right? So same thing we saw last lecture, and also there was sort of hints of that. There was hints of that previously. If we jump back sort of slides, I'll restore this. Yep. If we jump back a lot of slides, yep, to these. Where was the contour map? I had it. Oh. If we jump back to sort of slides, we sort of saw a hint of this, namely that the principal axes were uneven, right? It's a very, very slim ellipse. So because of that, you're pretty much guaranteed, if you raise the learning rate too much, you're guaranteed unstable behavior, especially with a fixed learning rate like I was doing. And so we learned ways to counteract that. Assuming I was less of a lazy programmer, how would I counteract that? And I still wanted to have fewer iterations. So I wanted to make the learning rate larger. But is there a way that I can make the learning rate larger but have less iterations but still keep it stable? Yeah, please. Yeah, so you could adjust the step size. You could adjust the step size. You can make the learning. Okay, so I should have specified. So I could if I make the learning rate larger initially, but adjust the step size using Amijiro's condition. That's an option. Also, you could use momentum, right? That's probably what most people would do in this case. They would use momentum, and so momentum would help stabilize things a lot, even with a fixed learning rate. But you know, this is just a proof of concept. There are always optimizations to make. Okay. So, sorry, zoomed in. There we go. All right. So that's how we use the gradient descent. That's how we use gradients. That's how we use gradient descent to calculate the optimal, the optimal solution to the data. There is one of the nice things about linear regression is that we have more than gradient descent available to us. Namely, there is actually a closed form matrix solution to the optimal equation. So remember that expression we came up with before. This is literally just reformulating the derivative with respect to the partial derivative of the loss function with respect to the parameters This is that formula we came up with before. So what's nice about this is that this we could transform into a matrix form to get a very clean closed form solution to the weights, to the parameters. Namely, we can simply, this term right here is simply x transpose times x. This is x times x, right? So if we want, since we are simply multiplying x times x, we could simply do that. You have matrices, right? We don't need this summation. We could do simply a matrix multiplication and get this same effect here by doing x transpose times x. So this covers the two summations times w. Okay, so this sort of expression here, we could rewrite this whole thing as x transpose times x times w minus x transpose times the target. Right? That's all we're doing here. We're multiplying each value of the input times the target. That's all we're doing there. And we have to set that equal to 0 because the minima occurs when the partial derivative is equal to 0. Okay? So knowing that, and having this function, and we get rid of this, and this 1 over n term falls apart because we set this equal to 0 and we multiply both sides by n. Okay? So knowing that, we have a very clean little equation for very clean little equation for w, right? Because we know all the values of x, all the x values in the data set. We know all the targets in the data set. So really the only unknown in this expression is w. So in order to get w, we simply move this over to the other side to get this expression. And then in order to get rid of these two, we simply multiply the left side of both sides of equality by x transpose times x to the negative 1. Okay? And then doing this, we get w is equal to x transpose x to the negative 1 times x to the times x transpose of t, of the targets. Okay? So, I mean, when you first see this, you could trust me, but I wouldn't trust me. I could say anything right now. You shouldn't necessarily trust me. We should test it out. So we could test it out. And in fact, if we test it out like so, if we test it out and we literally have x, which is all the 10 points, we have the not ground truth, targets. We have the targets like so, generated using the same seed as before. This is a vector, this is a vector. And so we want the bias. We want to know the bias. So we add the 1s to the bias. We add the 1s and append. We have a 1s column to account for the bias, then append that to the x inputs. Okay? To get the full vector. And then all we do is say w is equal to the inverse of x transpose times x transpose times t. Matrix multiply all of them. And if we do all of that, and actually I just left this in for debugging. And if we do all of that, we see that the bias is equal to 5.96 and the actual slope is equal to 2. And that is the absolute optimal, that's the absolute optimal parameters for the function, for the y equals mx function that describes the data set we have. Okay? So it seems to work pretty well because, again, the data set we calculated was using a slope of 2 and a bias of 5, and we added in some noise, so we can't expect it to always to be dead on 2 or dead on 5. And in fact, that seems pretty reasonable. Seems reasonable, approximately correct if we include the noise. Okay. Make sense? So everything works out. So, I mean, so the real key is that the amazing thing about linear regression, about linear systems, is that you could solve for the optimal values exactly, right? This is how, you know, before gradient descent was everywhere, before, well, I mean, gradient descent has been around for decades. I mean, pretty much since the dawn of computing. But before, like, machine learning was everywhere, you know, when we had to do regression analysis in our physics class, when I had to do it, like 20 years ago, regression analysis by having a bunch of data that we collected and then having to plot a line. When we did this in MATLAB, you know, MATLAB didn't do gradient descent, right? When it's trying to fit a straight line, it doesn't do gradient descent. Even when it's trying to fit a parabolic line, it doesn't do gradient descent. It simply does this equation, this optimal equation, and bam, it gets the optimal value, okay? And that's the beauty of linear regression, is that linear systems are easy to solve for in a way nonlinear systems are not easy to solve for. So knowing that, knowing why when we had a matrix solution, why do we do the gradient descent? Why do we even bother with gradient descent? I'll let that one hang for a minute. Yeah, please, Kobe.
Works for nonlinear systems?
Yeah.
That only works for linear systems?
Yeah, exactly. So gradient descent, the beauty of gradient descent is it's applicable to a wide variety of systems, right? And even as we saw last time, gradient descent even works fairly well, and it doesn't always work, but it works fairly well for even non-convex systems. And that's not 100% true. You'll see examples of that. But for the most part, that's the beauty of it. Gradient descent is robust. And I think one of the things that it's easy to forget with computing is that robustness matters a lot. One of the reason why, I mean, across the street, and not to disparage them, but across the street, every professor that is in electrical engineering has come across some new device that is so much better than MOSFETs, that uses less energy and is faster and whatever as MOSFETs, right? These papers are everywhere. My PhD topic was on one such device. Now, the reasons MOSFETs have basically revolutionized everything and are pretty much going to stay pretty much a staple of computing: robustness. Voltage, the idea of voltage is robust. Currents are not robust. Currents have noise, voltage are robust. Same thing with computers. The most popular algorithms that we use are the most robust algorithms, gradient descent. These specialized algorithms are wonderful, especially if you're writing a research paper. It's like nice to have an algorithm that solves a particular problem in more time. But communicating these algorithms to more people, to a wider audience, has costs. And having checks and balances that says, okay, if a system is exactly like this, then I could use a special algorithm. That's a lot to program. And really, robust algorithms sort of win the day over time. So that's why gradient descent is wonderful. And you know, linear regression seems pretty great, but again, why bother with anything else? And we bother with other things because not all data will be linear. In fact, most data is nonlinear in the modern world. So that's something we'll discuss next week. Okay, I think it's a good place to end. All right, have a good weekend, guys. Oh, last minute questions? No? Okay, have a good weekend, guys, and don't forget homework 3 is due Monday. And there might be a delay on homework 4. There's a little bit of a technical issue, but I'll post on Piazza if there is. Thanks.